So the information about the complex material assembly is in the module handbook. And what I've got today is a slightly enlarged briefing session on that. And there is a briefing document that just gives you a little bit more information. But the sort of main information you need to know is in the module handbook. So the first key thing to note is the submission date, which is Friday the 20th of March. Okay? And that is a digital submission to Mole. So we don't need any paper copies of you for that. So there's detail in the module handbook about the submission, and it's got the full information about how you need to submit it onto Mole. Okay, so you can just read that. It's all fairly straightforward. The benefit, I think, of you submitting digitally is you don't have to wait in a print queue. You can just submit a digital copy. You don't need to necessarily, spend money printing if you don't want to. And the students asked for it last year. Could they just submit digitally? So fine. What I should explain though is the submission is 2 to 4 A1 files. So even though you're submitting digitally, they still need to be an A1 file. Okay, obviously digitally that doesn't mean anything, but you need to work on an A1 sheet of paper so that if you were printing at 200 dpi or 300 dpi, it would print at A1. All right. When I come to mark the work, I will use, we've got these new 4K TVs, which are full high definition. Okay. They're about A1. So if you put an A1 PDF on those, they view about like an A1 piece of paper. So I will be looking at the full detail that you put into your submission. So don't think that because you're submitting digitally, that I'm just going to mark your work on my little laptop screen here. Okay? I will look at the full quality. So just think of it like an A1 piece of paper, basically. And then, that will work for you. What that does mean is, because it's A1, it's not A3, so don't have enormous text. Think of it as an A1 sheet of paper. It's very important. Okay. So let's go into the more detailed briefing document. This will go onto Mole later today. So I will go through this today, but at times I'm going to just summarize it and skip over things, okay, on the assumption that you'll go and read it in detail in your own time. Okay. So, complex material assembly. In this submission, you will explore assemblies arising from your emerging projects. You will begin to test the relationship between physical assemblies and materials through design. So just to give you a little bit of background to the CMA, we've been running this project now for about 6 years, and I implemented it because we were finding that the sort of project technology, it was getting left to the end. So students were thinking, project technology was just sort of arriving in the last week of the project. And then when it arrived, it was often very kind of functional. So we were getting things like gutter details, foundation details, very sort of standard generic construction solutions, which didn't capture any of the kind of specificity, any of the quality of the project. So we had to have a rethink. And so what the complex material assembly has done is it's brought a thinking about technology earlier in the project. And we deliberately, we start you now working on it, in semester 2, because we want you to start that engagement with technology. And to see technology as something which is very much project specific and not generic. So we're not interested in kind of typical generic construction. We're looking for you to explore a project technology which is informed by your project by your studio, by your approach. Okay, and we encourage a degree of experimentation in the submission. We've placed, the submission's quite early on, so we've got plenty of time afterwards. We do credit experimentation, so when we're marking it, we're not looking for you to play it safe, particularly in 5th year. We're looking for you to try things, to research new things, do some kind of wild and wacky stuff if you want, and see where that can take you in your project. And we've found over the years that it's been really successful, okay? And the students have kind of responded to it. The quality of the technology work has improved dramatically, but more importantly, the technology has become really kind of interesting. Often it's researching new areas, it's trying some kind of really unusual approaches, and then working that into a project. Also, the quality of presentations gone up massively. Okay, so it's felt like it's really helped your project work. Now in 5th year, you're a bit freer in your project and in your design, and you're not sort of heading towards the year 6 thesis project. In the year 6, often the CMA work is very much becoming their project work, so it's informing their architecture. Okay, so just to go into a few things here, I've got a bit of a cold, I'm afraid, so you'll have to bear with me. Why complex? I've had a few discussions over the years with students, sort of, questioning why we're calling it complex material assembly, or why complexity, and the kind of reason there is that it's not because we're pushing a certain kind of complicated architecture or a complex architecture, but we want you to embrace the complexity of project technology. Okay, I'm just going to quickly show you a video here. And this video is, I hope it's kind of demonstrating that even a very simple architecture, a very pure minimal architecture, the complexity behind fabricating and creating that architecture is immense. So this is a Tadao Ando project, and I'll jump into a little while. It's going to show the kind of complexity behind making that very kind of minimal Tadao Ando bare-face concrete. I'm just going to skip to... So you see this is time-lapse images of the construction of this concrete. So you get a kind of idea of the complexity that's involved in terms of construction, in terms of organizing people, site, materials, for what in the end, as you'll see, is a very, very pure, minimal piece of concrete. And this is, I think for those of you who have a project where the technology is very simple, what we try to do is get you to embrace the complexity of the process. Let me just jump forward a bit. So I'm just going to jump forward to making the wall here. So this is the shuttering going in for the concrete. The tie bars going through. It's all propped. And at some point they're pouring the concrete. There we are. Concrete's gone in. They've stripped it off. And let's go back and stop that. Okay, so I thought that was a kind of nice example of, very, very simple architecture. but there is an inherent complexity in the process. Now, for some of you, you may have quite complex technology anyway. But that was just a response because I think some students were a bit nervous that we were pushing them in a certain direction architecturally, but that's not really what it's about. Okay, there are examples on the CMA website, which I'm sure some of you will have already seen. Let's have a quick look at that. And I think this is a very good way of getting a feel for the kind of work that's been done, the kind of approach, the way of setting out the work. So just to quickly show you a few things about navigating the website. If you click on the page, click on the drawing, it will enlarge it. Click on it again, it will enlarge it further. If you want the full resolution, because these are, bearing in mind these are A1 images, then you need to click on the PDF link at the bottom. That will open the image in the Google Doc viewer. And through the viewer, you can download the full quality, the full resolution image if you want. Okay. So if you really want to study any of these, you'll have to download it, because that's the only way to read the text in some of them. Okay. So have a good look through here. The submissions are arranged by theme. So you can have a look under different themes and see what kind of work might be interesting to you. And there's some fantastic examples on here. We'll have a look at some examples later. Okay, distinction between Y5 and Y6. So at Y5 level, you may be pursuing a building design, or you may be pursuing a more research-based spatial design. And as such, you're expected to align the CMA with the spatial research question in your studio project and use it as it means to develop your spatial design. So at Y5, you may choose to develop a discrete element, a small part, a component. You may wish to investigate a material process, an assembly process. It's a bit freer, basically, in year 5. In year 6, we push the students to take a part of their building and explore it, like a roof or a facade or a structure. And that's partly because we want, in year 6, we want the CMA to help them progress their project. Okay? But in Y5, there's a lot more freedom. Okay? And it can be, this can be a very experimental phase, or it might be more about kind of building technology. That's very much up to you. Okay? I forgot to say, references, you can have a look at that in your own time. There is a technology references website which has a number of useful documents in there. Okay, so some of the key aims of the CMA. I'm just going to summarize these. Okay. So firstly, ensure that a process of engagement with the physicality and materiality of your project has started. Okay, so it pushes you to engage with materiality. All right, you can't avoid it. Okay, so that has to arrive in your project. We push you into that now. It may feel uncomfortable because you may think, well, I don't have a design yet, but we push you into that. Promote a non-linear mode of working in terms of scale, concept, and detail. So what I mean by this non-linear mode of working is, we don't want you to follow a traditional route of sort of, let's say, site study, site layout, scheme design, building design, detail design, materiality. And, that would be a kind of traditional route you would see in a School of Architecture, where any kind of detail assembly work or detail construction or materiality, it would come at the end. And it would be seen that you can't explore that work until you've developed and designed a full building. Now, in CMA, we push you to mix that up. You can explore detail early on in a project. You can explore materiality even though you don't have a building design. It doesn't have to follow that kind of linear route. Okay. Promote experimentation at the level of assembly and materiality. So we want you to try things out. We don't want you just to go to the library, find those standard details, and say, right, well, that's how you do it, I'll use that. We want you to experiment. And we want you to experiment at a level of assembly and materiality. So, physical materiality of your project, putting things together. Promote experimentation and creativity in terms of project-specific environmental approaches. So for some of you, CMA will allow you to start to explore some kind of creative areas in terms of environmental design. Understand the relationship between building assemblies and their impact on the environmental performance of the building and the wider system. So again, in exploring assemblies, exploring materiality, you can start to consider the environmental impact of your design decisions. Develop an awareness of the creative role of environmental testing as part of design methodology. So not for all of you, but some of you, you may start doing some testing of your proposals. Okay, use three-dimensional tools and techniques to explore the intricacies and realities of material assemblies. So we have a big push here on three-dimensional exploration. And that might be three-dimensional models, it might be three-dimensional computer models, it might be working with material models, with real materials, but we try and push you to engage now in 3 dimensions, not just 2-dimensional sections. Develop an understanding of the structural methods of assembly, commonly and less commonly employed, and experiment with untested methods. So we want you to think about assembly. How in a building do you start to assemble materials? How do you fix things together? Okay, there's a whole kind of cultural significance there, how you fix things together. Finally, complete a portfolio standard piece of creative, project-specific technology that will inform the development of your wider studio project. So 2 things there really. 1, the submission will be portfolio pieces of work. They're A1 sheets, they should be a good quality, they'll go in your portfolio, they'll be part of your final submission at the end of the year. And secondly, you're developing your project through this. So hopefully it's not seen as something kind of additional, it's not an additional piece of work, it's seen very much as you developing your studio project. Okay, so possible themes. Now, you're not limited to these themes. What these are is looking over the years and grouping the kind of work into a number of themes that seem to be the most kind of common areas for exploration. And these are the themes that are used on the website. Okay. You don't need to choose a theme, but it's important to just think about what kind of area your investigation work is in. So, specifics of assembly. Thinking about assembling materials, components. The cultural significance of working with, connecting, and finishing materials. So, that's really important, that the way that cultures have assembled materials is not generic. The way we might fix timber together in the UK is completely different to how we might put timber together in India, let's say. Culturally embedded technology. So in this case, physical models, constructs, detailed drawings will be important, and the role of the maker is embraced. So if you're thinking about assembly in a project, who's assembling it? Is it a contractor? Is it Is it a sort of resident? You know, who's putting that together? What skill level do they have? What's their understanding? Materiality. So, developing material interests. Looking at the properties and characteristics of materials, maybe experimenting with new uses. You may consider material transfers, where you're taking material that is normally not associated with architecture and you're bringing it into architecture. That can be quite a rich area. Thinking about lifespan, possibly, and possibly thinking about testing. And that's why I put this note. You might need to get messy. You might need to get your hands dirty. We've had some great experiments in the past where students have they've gone out, they've got some materials, they've made stuff, they've mucked about with it. Here we've got, I'm sorry you can't see it because the projector's gone a bit wrong, but the top project, the student was setting fire to wood. So they were making things, they were burning it in different ways and seeing the effects on that wood. Really kind of interesting approach. And then the bottom project was the student was looking at admixtures to concrete, primarily scented admixtures. So they were making a scented concrete. And they decided the only way for them to find that out was to actually go out there and make some scented concrete. And they made all these samples and they took it around the studio and asked people to smell it and fill out a survey. It was great. And then, this became part of the project. So, really interesting work. Now, at Y5, you've got a good level of freedom. You can kind of go and explore what you like with this. In Y6, we tend to push them a bit more into developing details, but for you don't really have to. So have a look at some of those material examples, some interesting work. Okay, structural specificity. So structure may be a very important part of your project. And the critical relationship between structure, environment, envelope will be explored. You may consider adaptation, degradation, disassembly, reuse. You may look at connections of structure. You may explore some new structures. I'm not sure if it's on here, but there was a great project a few years ago where the student made cardboard beams, one-to-one, full-scale cardboard beams, got them in the studio, got people to sit on them, jump up and down on them, and it was fantastic first-hand research and experimentation. Or, more like the examples here, it might be more of a kind of paper-based exploration where you're perhaps using computer models, 3D assembly models to develop the structure of your project. Process and production. Explorations into the complexity of processes involved in the production of architecture and their specific relationship with the architectural language and meaning. Cultural and vernacular influences. Exploration of the complexity of construction, so that the specifics of sites, the working methods of teams, the whole idea about building, about constructing, getting under the skin of that process. This is a very important one. The specifics of budgets. Money. How much money have you got on your project? That can be a hugely creative design generator. If you've got a limited amount of money, it can force you to work in incredibly creative ways in terms of technology or materials. And, health and safety. You may not think it's very exciting, but it can be a really creative generator in a project. So, just some ideas that you might wish to explore. Prototyping. So in some cases, your technologies are untested. And the only way that you can really imagine those technologies in an architectural project is to consider prototyping. And there could be two forms here. There could be you actually prototyping construction, so building it, testing it, maybe a scale version of it, maybe a sample of it. Or you may move into prototyping, where prototyping forms part of your project, as in a kind of imaginary prototyping, but that becomes part of your design project. So, this can be a very rich area. You can't really see it, it's far too small, but that example there was the student prototyping some pneumatic shading devices. And they built it. So rather than just exploring it as a drawing, they actually got plastic bags, they did some research into pneumatics, they built this thing that would move when they changed the air pressure in it. Really, really kind of interesting work. And obviously we've got 3D printer, we've got laser cutters, we've got a CNC router. So there's some good equipment there that for rapid prototyping, which can be very helpful. Optimized facades. So all buildings have a facade, and for some projects that can be a really interesting part of the technology. And that could be in terms of environmental performance. It might be about materials. It might be about the kind of evolution of that facade changing. But the idea of kind of optimizing a facade for performance. So designing it, changing it, improving it. Okay, so that's some of the themes that commonly explored. Any questions before we look at a few examples? Okay. Let's have a quick look at a few here. Okay, so let's look at this one. So this was Guy Molson from a couple of years ago, and Guy was very interested in sort of experimenting with facades and with processes. He was really interested in the relationship between physical models and digital models, digital production, and so his CMA was a very kind of experimental CMA, and this was actually a 6th year CMA. It was pretty risky for a 6th year, I suppose. But so he was making these models, he was making these 3D meshes of those models. Let's go back to his other sheet here. And then what he did do is then turn that into an assembly which became part of his building. So this was it's a 3-dimensional computer image where he's taking some of those kind of skin ideas and making a component. Just to look at the layout on the sheets here, in this instance, he's giving that drawing lots and lots of space, really detailed, high-resolution image, so he's giving it virtually the full A1. At the end of the year, this was one of his main drawings on the wall as well. And then, quite successful, Guy's putting some of his little sketchbook extracts down here. Let's go into another one. Nicola, this was a slightly more conventional approach, I suppose, where she started with some material studies, and she was interested in light diffusing concrete and I think sort of embedding different materials into concrete. So she made all these samples, playing around with concrete, putting fibre optics in, putting glass in. These are actually precedent studies from other projects. So she's, this is quite important. You can put your references on the sheet. It doesn't have to be just your work. And then she made this mock-up of a translucent concrete facade. And then when I say it was quite conventional, it was conventional in the sense that she then took that material study and applied it to her building. So, fairly sort of straightforward. It became part of the cladding. So we've got this very nice, very good quality axonometric, which is showing the construction and the materiality. And on the same sheet, we've got all these very rich material studies that are kind of exploring the qualities of the material. And there were actually two sheets, so both kind of similar, but this was a more two-dimensional. Okay. This was Tom from a few years ago, and Tom's interest was about setting fire to the facade. So he started making these little scale models out of bits of timber, and then he did set fire to it, and he photographed it, he drew it. So as you can see on this stage, on this sheet, there's no building as such. So it doesn't have a shape, he doesn't have a facade, but he's still exploring this idea of shingles. And what he's done is just make a kind of a fragment. So he doesn't really know what it should be in terms of shape, but he can make a fragment of it to begin the experimentation. And where that led him, on the next sheet, I'll just zoom in down there, some of the outcomes of that kind of burning pattern, where he then left the models out in the rain and the sort of the black burnt bits kind of washed down the facade. And that led him to this drawing where he wanted this kind of streaking effect. And he then moved on to make this sort of newspaper facade model, where, again, at this stage, he doesn't really have a building. He doesn't have a building plan. But he started pursuing this idea of a kind of wrapped facade that you could almost detach from the building. So, really great investigation, and this became his architecture. And his building at the end of the year, very much looked like this. And, which was great, because it was so project specific, and it was coming out of his material studies. It wasn't coming out of looking at other projects and kind of copying bits. It was very kind of unique to him. Let's look at a few more. So this one was all about assembly, and what this student did was they used the CMA to develop a really important part of their building, which was a sort of projecting bay window, I think, where a sort of writer could sit and do some work. So the first sheet, hand sketches, little explorations, a few smaller study models. And then you can see the other three sheets are all about getting into a really sort of high level of assembly detail. Really getting to grips with how every component is fixed together, the full assembly. So making really great use of exploded drawings, detail studies, little computer renderings, to fully understand the materials and how they would be assembled. So there were, as I say, there were three sheets of that, and what was good here is, because the student tackled a discrete, independent element, they could really get into the detail of it. Whereas if you tackle something too large, you can't kind of get into that level of detail. This was another material study. Again, looking into concrete. And this student was making concrete formwork and exploring different kinds of release agents and looking at the kind of impact on the concrete. So that was a kind of material study, and then that then moved into actually applying it in the project. And so the final sheet here is taking that kind of concrete quality and actually applying it as a sort of detailed proposition in the building. And again, we've got precedent here, important precedent. We'll put it in the corner there. Okay, I'm not going to go through any more examples because you can have a good look in your own time now. Okay.